This presentation is going to be on water potential and water movement. So we have a few terms to be introduced to. Hypertonic is in reference to more stuff. Isotonic is in reference to same stuff. And hypotonic means less stuff. Okay, so hyper means more stuff. So if we have more stuff in the solution outside of our cell, what's going to happen is molecules of water are going to want to move out of the cell from an area of higher concentration of water to an area of lower concentration of water. So we have more, let's say this is a salt solution out here that's higher in concentration of salt than the cell is. So we have now a higher concentration of water inside, it's going to want to move out, and the cells are going to shrink. Isotonic means we have the same concentration of stuff on the inside and outside, and so the cells are going to stay the same size. Water is still going to move in and out, but it's moving in and out at the same rate, and so it pretty much looks like nothing's going on. Hypotonic means we have less stuff on the outside, so we have a greater concentration of water on the outside, and therefore water is going to want to move into the cells, and when water moves into the cells, when they're animal cells, it will cause lysis. It will cause the cell to rupture, and that's not good for our cells, and so we try to keep the concentration in our blood cells and in our blood plasma pretty much identical all the time. That's why when they give you a IV, they use a saline solution instead of pure water, so that those cells have a similar concentration inside and outside. All right, now with plant cells, we got a little different thing going on here. So if we think about a plant cell, the plant cell is not going to rupture because the plant cell has a pretty sturdy cell wall. So it's got a plasma membrane, the cell membrane's right inside the cell wall, and then it's got a sturdy cell wall. So as water tries to flow into a plant cell, the pressure might increase inside here, but the cell is not going to rupture. So let's talk, we'll look at a Elodea plant. This is a seaweed, and if we look at these leaves, they're pretty transparent, and if you look at them up close under a microscope, and we have that plant cell in pure water, what happens is water moves into the cell and it causes the cells to swell, but they don't rupture. The water pressure pushes against the cell wall, but there's no rupturing going on. So this is what we see if we have it in pure water. If we had Elodea in a solution that was similar to the inside of the cell, it would look more like this, where they're not swollen, they're just kind of steady. And then if you put Elodea in a salty or sugary solution, what's going to happen is the cell walls and the cell membrane is going to pull away from the cell wall, and it's going to shrink and form little balls, and it looks like this. So this is the cell membrane. Here's our cell wall, but water left, and so that membrane pulled away from the cell wall, and now the cells kind of all compact. Because the cell wall is pretty sturdy, it really doesn't move, but the cell membrane is flexible, so it can shrink like that. All right, so we're going to talk water potential now. So water potential is a way of calculating which way water is going to move. And it involves a couple of things. The sign for water potential is psi, and water potential is equal to pressure potential plus solute potential. If we have an open container that we're dealing with, then pressure potential is not going to be a factor. Solute potential will be the main thing we're dealing with most of the time with water potential, but sometimes pressure potential plays a role, and we'll talk about that in a minute. So how do we calculate solid potential? So solid potential is calculated by a few different numbers. The first number is whether or not that molecule ionizes in water. So if it ionizes in water, and like salt, it forms ions in water, then that first number is 2. If it doesn't ionize in water like sugar, then the I is 1. Okay, so this is just how many particles does the molecule make if we dissolve it in water. C is the molar concentration of the solution. So if we have anything dissolved in our solution, it's going to be, 0.1, 0.2, 0.3, whatever. It's going to be a positive number. R is always a positive number. It's always going to be 0.0831 liter bars per mole degree Kelvin. When we do these calculations, the liters, the moles, and the degree Kelvin will cancel out, and I'll show you why. And we always end up with just bars. And then temperature in degrees Kelvin. Since we're dealing with absolute zero now, there's never going to be a negative number here. So whatever our temperature is in degrees Celsius, we add 273 to that, and that's what goes into our formula. Okay, so this and this and this and this, these are all going to be positive numbers. Okay, so since it's the negative of 4 positive numbers that I multiply together, solid potential will always be negative. Solid potential can never be positive. The highest solid potential you can have is 0, and that would be pure water. So solid potential has to be negative. The only way it could be 0 is if I have 0 concentration of solid dissolved, and that would mean I have pure water. All right, so let's think about this here for a second. So if we have pure water on one side, it's going to have a solid potential of zero, so its water potential is 0 because there's no pressure. Open container, so solid potential and water potential are the same. And over here I have a solid dissolved, so now my water potential is going to be negative. Okay, so which way is water going to want to move? Well, water always wants to move from the higher 0 to the lower, the negative number. So water in this case would move across the semi-permeable membrane in this direction. It would raise this side up and lower this side over time. Obviously, your force due to diffusion and your force due to gravity are going to balance out at some point. But water would move from this side over to this side. Now, let's look at that calculation again. Sometimes pressure does play a role. I'm going to show you an example of that. So here we have distilled water. Okay, it's got a water potential of 0. And I'm going to put a plant cell into the distilled water. Well, initially, the plant cell has solids in it. Okay, so water is going to want to move into the plant cell. But eventually what will happen is pressure is going to build up inside the cell, and it's going to start pushing back, okay, on the cell wall. When that happens, now the force pushing back and the force moving in are equal, okay? So our overall water potential in this system became 0 again because I have 2 bars of pressure, okay, pushing out, and negative 2 bars of pressure wanting to move in. Okay, and so now my water potential is back to 0. So sometimes pressure plays a role. If you're dealing with like a reverse osmosis system for making drinking water, there's going to be a lot of pressure involved in that particular system. And so sometimes pressure plays a role in which way water wants to move. Now, this is probably one of the most important things as far as nature is concerned in water potential, is how do we get water from roots to the top of a tree? Well, one of the big things that happens in leaves is transpiration, water evaporating from the leaves out the stomata, okay, and into the air. So as that water evaporates out through the stomata into the air, you have water leaving the leaf, and water, because of cohesion, when water leaves here, more water wants to get pulled up into this leaf. Okay, so we have a bunch of forces working together here. We have transpiration or evaporation from the leaf. We have cohesion of water molecules that pull the water in this tiny little tube called xylem from the roots all the way up the trunk to the leaves. Okay, they're tiny little skinny tubes, and so there's not a lot of gravity that the molecules, that the water potential flow has to battle, because these are super narrow. And so having a difference in water potential causes the water to want to move up the tubes. And you can see over here, the outside air has a water potential of negative 100 megapascals. This is just 10 times what bars would be. So this would be like negative 1,000 bars. The leaf would be like negative 70 bars. The cell walls, or I shouldn't, yeah, the leaf cell walls would be like negative 10 bars. The xylem would be like negative 8 bars. The trunk, lower xylem, would be like negative 6, negative 5. And then the soil would be like negative 2 or 3. And so water wants to move from the soil into the roots, from the roots into the xylem, into the higher xylem, into the leaf cell, or into the leaves, and then into the, out through the stomata into the air. So that's part of how water moves through a tall tree.